In my latest attempts to make efficient RC planes, I constructed a 6'6" flying wing to fly the biggest batteries I own. These 10 amp-hour 4-cell batteries come in about 2 pounds 2 ounces, making the flying wing, or as I named it, the Kraken, just about 6 pounds. The plane flew so well that on my first real test flight with the monstrous battery, the Earth got real jealous and jumped right in front of me. Though, I quickly learned after this that flying wings on paper should be the most efficient aircraft with no body or tail surfaces causing excess drag. However, in practice, they have never been known to outperform a fixed-wing aircraft due to them having a high lift-induced drag. I put the scratch building on the back burner and turned to my factory-made Mini Talon, one of the hallmarks of long-range FPV planes. I don't mean your average trip across town and back. Here's a clip from YouTube with a hobbyist flying his Mini Talon over 100 kilometers out and back. That's 62 miles twice over. Around the same time that I crashed, I mean the Earth destroyed the Kraken, I found a project called QSEC LRS. QSEC LRS is a project to create a DIY RC link based on the SX1278 transceiver-based LoRa modules. LoRa modules find their home in many open source projects due to their simple sacrifice of high data rate for very long-range communication. While we can't use these to stream Netflix, we can, with the help of QSEC, build our own very long-range RC link for the 10th of the cost of a TBS Crossfire or a Dragon Link. I ordered 2 1-watt modules and one smaller 100 milliwatt module to use in my quadcopter. The next step was to flash the 1s and 0s with an ST-Link programmer, and voila! Just like that, after the firmware has been loaded, we can configure the module's frequency hop spacing, telemetry data rate, and so on. The final step in building the RC Link is to solder the necessary components onto the module. For both transmitter and receiver, a current limiting resistor, LED, and push button are soldered. A case hot off the 3D printer makes a nice enclosure for the module bay of the controller. Here we have an old 12 amp ESC acting as a BEC, providing a stable 5 volts to the module. Connecting the receiver to the Mini Talon's flight controller was pretty straightforward. Just configure a PPM input on serial port 3. Miraculously, the $8 RC Link is working, shown here with the corresponding channels moving accordingly. I then printed a pan tilt nose cone, landing skid, and RX antenna mount to tidy things up. To my disappointment, the all-up weight of the plane was on the inefficient side for the motor and prop combo that I have. To solve this, I found the type of airfoil that the Talon has, an E205, and printed 2 hot wire templates. I made my hot wire cutter from PVC pipe, a doorbell transformer, a dimmer switch, and a hairdryer for the nichrome resistance wire. The transformer had a 30 and 60 volt output, so I used a single pole double throw switch to toggle the output voltage. On the low side is great for foam, and the high side turns the wire red hot and can be used to cut plexiglass. This is the second wing I made from the hot wire, and they turned out great with only minimal sanding required. I cut the main spar in half and lucked out when I found an old tent pole fit perfectly inside the inner diameter. I then printed some bushings to allow for the smaller spar. A few small touch-ups later, and she was ready to maiden. As soon as I got into the air, I noticed something weird with the roll. It felt like steering a whale through the sky. After porpoising a bunch, I figured it out and leveled out flight. We'll skip to a part where I get a little bit higher. When I got some altitude, I did some tests for efficiency. It pulls just under 5 amps at 35 miles an hour. I can constantly monitor the plane via the on-screen display in my video goggles. Unfortunately, I forgot to press record for this mission, but here's a clip from one of my other planes. In the goggles, we can monitor battery voltage, current, radio strength, GPS coordinates, altitude, distance from home, airspeed, ground speed, all the good stuff. Right about here I turn the flight controller into return to home mode to test that, well, it returns to home in the event that I lose radio contact or any other failure. The plane did turn the nose around and headed back to the track where I was. We could calculate how long we could fly this in an ideal situation by simply dividing 8 by 5. 5 being the amount of current the plane draws at cruise speed, and 8 standing for 8 amp hours, which is a measurement of my battery's capacity. In real life, other factors such as air temperature, especially in the winter, affect the battery's performance. However, we can reasonably expect this plane to fly over 1 hour, probably around 1.2 to 1.4 hours. After these quick tests, it was time to put her down. That's when I noticed its pretty impressive glide slope. Considering this is a 2 kilogram flying brick, it was pretty good. Well, that concludes this video. Thanks for watching. Bye.